Welcome back to the Crunch seminar this week. And today we will have two speakers. So the first speaker will be Dr. Anirbit Mukherjee from the, he obtained his PhD in applied mathematics at the Johns Hopkins University, advised by Professor Amitabh Basu. He is now a postdoc at UPenn, working with Professor Weijie Su. He specializes in deep learning theory and has been awarded 2 fellowships from JHU for his research. And earlier, he was a researcher in quantum field theory while doing his undergrad in physics at the Chennai Mathematical Institute and master's in theoretical physics at the Tata Institute of Fundamental Research. So today he will give us a presentation with the title Recent Progress with Mathematics of Neural Training. And let's welcome Dr. Anirbit Mukherjee. Yeah, you can start your presentation.
Thanks, Andrew, for the very generous introduction. Thanks for the invite. Hopefully, you will find it interesting. So most of the work I'm going to present here is basically from half of it almost is from my PhD work with Professor Amitabh Basu and collaborators at JHU, and almost half, the other half is work over the last 1 year with collaborators Professor Shayur Karmakar at University of Florida, Professor Weijie Su at UPenn Statistics, and Panideep Gampa at Amazon India. So I'm not sure how familiar everyone is with neural nets. I'm assuming everybody here knows enough neural nets, but if someone has ever seen, here is one diagram to keep in mind. What you see on the screen is a computational graph of a very standard neural network. It takes 2 inputs, x1 and x2 as input on the green nodes. The top blue gate is a ReLU gate, which computes max of 0, x1 plus x2. So you can just compute through the edges weighted combination. It takes a weighted combination of the inputs weighted by the weights on the edges that you can see on the screen. So the second blue gate is a ReLU gate, which is computing max of 0, minus x1 minus x2, so on and so forth. And the red is the output gate, which is a summing gate, which takes a weighted sum of the outputs of all the blue gates. And you can convince yourself that this is a simple neural net which computes the max of 2 numbers. So here is a simple function implemented by a simple neural network of depth 2, because the distance of the input to the output is 2. And the width of this neural network will be set with 4 because there are 4 blue gates. That's my conventions. And in 2016, when we first started proving theorems about neural nets, this kind of max function computation was very important to the structure of neural theory. Like one of the first structure theorems we proved was that every continuous piecewise linear function is a neural network, which is of depth log n. So the space of all neural functions is exactly the same as the space of all continuous piecewise linear functions. So this is kind of the first characterizations of neural functions that we gave when we first started research in this direction. And these kind of proofs are very importantly hinged on understanding max function computation. There are many open questions still there are many questions still open about max function computations in neural networks. Okay. More generally, we would define the rectified linear unit, which is an activation function, which is an important part of how neural nets are defined. There are many activation functions out there, but this one is essentially the most important one, I would say, because it supersedes almost everything else in experiments. So, which is a ReLU function. It takes an n-dimensional, the ReLU function takes an n-dimensional vector as an input and gives an output as another n-dimensional vector by taking coordinate-wise max of 0, the input coordinate. And the most usual class of neural networks that we write proofs about are what are called feed-forward neural networks. So what is a feed-forward neural network? It is essentially a composition of affine transforms with ReLU functions. So what you see on the screen in red is a depth k+1 neural network, which is first an affine transform A1 composed with a ReLU on the output of it, then an affine transform A2, and this alternates. And number of affine transforms is k+1. And you can convince yourself that in the computational graph picture, I define depth as the graph distance between input to the output, and the graph distance is the same as number of affine transforms. So depth of neural network can be defined in 2 different ways, either as number of affine transforms or as the computation graph distance between input to the output. And people also define width of a neural network, which is typically defined as the largest of any of the dimensions of any of the affine transforms occurring in the sequence. So the affine transforms could be of different dimensions internally. There's no restriction on what the input and the output dimensions could be of any of the A matrices or the A transforms. Whatever is the largest dimension occurring there is the width. But we should clarify that this is not the only class of neural networks out there. There are many more complicated classes of neural networks which won't fit this definition. So that is not our focus of research at this point, because we believe this is already hard enough for most important questions we want to ask. That there are a lot of other neural networks which will not fit this definition. And we probably need to invent new theory for them, which is not within the scope of my research at this point. But why are these functions interesting? So for someone like me, I get very excited by experiments like this. What you see on the screen are not photographs of any human, actual human being, but these are outputs of neural networks. It was possible to come up with affine transform sequences such that when it was given as input a random Gaussian vector, the output of the neural network was a human face, which is almost realistic looking, as if it's a photograph of another person. And this kind of things make me very interested. Okay, why was it possible to search out such affine transforms? How is it even possible that these exist? So mathematically, this kind of experiments need a different framing, and formal framing is required. So formally, we think in terms of the risk function. What we define are two kinds of risk functions. One is the empirical risk and one is the population risk. So given a distribution D, you take an expectation over samples x, y from the D of a loss function L's evaluation on y, n of x, where n of x is the output of the neural network n on the input x. If the distribution is, if you take the expectation over the full distribution, we'll call it the population risk. And if you take the expectation over a uniform distribution supported on a finite sample of the distribution, then you would call it the empirical risk. And that is the LS cap, and the population risk is LD, what you see on the screen. So the connection between LS and LD is the core of deep learning theory. All of deep learning theory essentially tries to understand when do properties of LS transform into LD. Like one of the most important questions about deep learning might be to ask, why is it that so often LSN is very, very low, nearly zero, and at the same time LDN is also nearly zero. So getting both of them simultaneously zero is one of the—
Anirbit, you confuse me. You confuse me in this slide. What are you saying? What's new? New to what? You said it's in a new avatar. Defining what is the? You're just talking about the landscape of the loss function, right?
Yes, I'm just defining a landscape of loss function.
Okay, two verbose for something simple. Please go on.
Yeah. So this is the landscape definition. So the core question of deep learning is, what are the classes of N, D, and L for which low risk nets can be provably found and easily and fast? So this is the main question of deep learning. We don't have very good understanding of what are good triplets, NDL. What are the good triplets NDL for which this search is easy and fast? And that's the main problem we want to understand someday. So to get a view of why this problem is hard, one should look at an actual picture of a loss landscape. So what you see on the screen is an actual photograph of a loss landscape. And you can see that the two diagrams you see are two-dimensional projections of a loss landscape, and they actually differ very little in terms of architecture. So it gives a hint of where the complexity comes from. And very little changes in architecture can dramatically change the landscape you're optimizing over. The right-hand side is a very smooth landscape, and it seems plausible that something simple might be able to find a dark blue point, which is the global minimum. Whereas the left, it's not obvious why you should be easily be able to find it. And this is where the designing of the algorithms comes into play. How you choose the setup so that your algorithm can find is very critical to how deep learning theory is framed. So real life questions can be framed in this risk function language. And that's like self-driving cars can be framed as a risk function optimization problem. And that's part of the magic here. And more generally, we don't want to do just arbitrary risk minimization about a distribution, but often enough, our setup is that the Y labels are actually noisy evaluations of some underlying function F. And then we want to say that we want to find a neural net in which minimizes the risk by actually approximating F. So it discovers the generative model. That's often the more useful framing of the problem, rather than saying over some distribution D, I'm going to minimize it. And the overwhelming evidence that this is theoretically, that experimentally this is possible. But there are lots of Fs for which you can design architectures which will eventually approximate F. And we don't have understanding of why this is possible. And one of the first proofs towards this was written by us in 2018 in the context of sparse coding. Let me quickly review the sparse coding result that we had. So sparse coding generative model is when you're seeing low dimensional linear transforms of high dimensional sparse vectors, which are called X star here. And I am seeing Y, which are A star of X star. So given lots of samples of these Ys, I want to recover A star. So how do you recover the dictionary A star? By looking at images through it of high-dimensional sparse vectors. And one of the old conjectures in this field, going back to 1970s almost, probably by Olshaus and Feld, was essentially to set up autoencoders to do it. So what is an autoencoder? What you see is an underbrace equation in the underbrace is an example of an autoencoder. It takes Y as an input, passes it through an affine transformer matrix W, takes a ReLU, and again passes it through a W transpose. Its input dimension and output dimension are equal. That's why it's an autoencoder. More than that, it's two layers of the same matrix W. So it's a weight-tied autoencoder. And it has been believed for a long time that weight-tied autoencoders are good mechanisms to discover dictionaries of possibility. But this has never been proven. So we were the first group in 2019 to give an evidence towards that, to say that you can compute the gradient of this function. It's a very complicated calculation, and show that it's actually asymptotically in the width, critical in the neighborhood of A star. So this is like a first proof of principle. Because if you can't even show criticality, there's very little chance you can get convergence of any algorithm to that point, any gradient-based algorithm to that point. Now, and then we showed experimental data that not only is it critical, not only is it provably critical in high dimension, a high width limit, but it's in fact a local minima. And for all we believe, it's actually a global minima. The true dictionary is probably even a global minima of the autoencoder loss function. And this has still not been proven. And building on a proof, Chinmay Hegde's group at New York University were able to show about a year later that actually gradient descent converges. They essentially used our computation and were able to improve on it to get a convergence of gradient descent. But it is still an open question to show that the original dictionary is actually a global minima of the autoencoder loss function. This part is still open. So this is one kind of research. But let's look at more carefully about how these algorithms actually work. So these algorithms are typically what are called noisy or stochastic subdifferential descent. So subdifferential descents essentially take some motion of gradient of the risk function and add noise to it in some various possible ways. The noise is what I call the Zt in the screen. So you take the subdifferential, add noise to it, and add it to the current value of your weight, and you update it. And you keep doing it again and again. That's a subdifferential descent algorithm. And these are very mysterious at this point, because we don't know why should the subdifferential descent converge to the global minima of the risk function. There is no mathematics at this point I'm aware of which can explain this. And this is one way I would say that is the core of deep learning problem. And these risk functions are non-convex, and they're even non-smooth. So despite non-convexity of the risk and non-smoothness of the risk, you still have subdifferential descent, which is essentially a very trivial algorithm converging to the global minima. And to explain this is, I believe, the fundamental deep learning problem. And to hint towards what is more generally done is not just subdifferential descent, but what you see on the screen, where I'm saying that the vector by which you're modifying xt, the iterated time t to get xt plus 1, is some vt. The vt is a very complicated combination of many other gradients you've seen till date. And that is what is often actually more successful than just vanilla subdifferential descent. So then the question gets even harder. Why such a peculiar combination of subdifferential seen till date is the right direction of modification of the current weight? And the questions keep getting harder that way. And we do not, and non-differentiability, non-convexity, as I said, only adds to the problem. So in recent times, there has been a couple of mathematical developments trying to explain this in general. One of the most important papers in this line, I would say, is the paper from 1804, paper that I referred to here, by Damek Davis, Shrivastava, Shyam Kakade, and James Lee. They were able to show that stochastic subdifferential method actually asymptotically goes to the stationary point of a huge class of functions, which include neural losses. And this is sort of the most general result out there that is known, as far as I am aware of. And the key mathematical idea they used to come up with this proof was to generalize the idea of differential equations to differential inclusion equations, where you say that I'm going to look at integral curves, which are solutions of dz dt is an element of the subdifferential, negative of the subdifferential set at the point. If you generalize the idea of differential equations to subdifferential inclusions, then you get a framework to analyze how this works. And they also needed assumptions about all paths of descent. There exists a paths of descent from everywhere. But still, this does not give a non-asymptotic guarantee. Even in this setup, non-asymptotic guarantee is still not. This is one of the most general results, but we still don't have non-asymptotic guarantee. Essentially, the same group in 1912 paper improved this result to get to local minima for weakly convex non-smooth functions. But still, does not cover neural networks, because neural networks are not weakly convex non-smooth functions. So we see that despite the general results being exquisite complexity, they are not able to capture the dynamics of gradient descent on neural losses, which is successfully getting implemented by every deep learning software out. So one of the questions we asked in 2016 initially was to say, okay, let us not do gradient descent. What if is there any algorithm out there which I can write down, which will get me to the global minimum of a neural network? And this is an interesting question to ask. And we came up with an algorithm which gets to the global minima of any depth to neural network for any training data. And that algorithm has a runtime which is exponential in the input dimension. Exponentiality in input dimension is expected because that's the NP hardness barrier. But surprisingly, it was polynomial in the training data, which sort of kills the conjecture that there is no NP hardness in the training data space. And at that time, we didn't have a good explanation about whether the width exponentiality of the algorithm is avoidable or not. But very recently, there has been a result which has shown that our 2016 result is in fact near optimal. So now we know that, okay, it's conditionally near optimal on some conditional complexity conjectures. So if certain complexity conjectures are true, you can sort of from there derive that exponentially in the width in our 2016 result is almost uneven. So at this kind of results, I'm not sure if it's completely known at high depths yet or not. At high depths, I think it's somewhat still open if there is any algorithm which given any amount of time will get to the global minimum. So this is one end of the theory. Starting late 2018, there was essentially a big upheaval in deep learning theory by the groups of Chen et al., Alan Zhu, and Simon Du et al., who showed that if you consider width of Arbit of sizes which are polynomial in the sample size and 1 over epsilon, where epsilon is the target accuracy. If epsilon is the target accuracy, look at nets whose size is 1 over epsilon to the power of 40. It's huge nets which are scaling with inversely with epsilon. If you look at nets of that size, there are a set of papers in 2018 we were able to show that SGD will get to linear time convergence to global minima. This is a very surprising result in a sense. So these two results that you see on the screen are like two extremities of the theory. One end you have high runtime global minimum of arbitrary nets of certain depth. On the other end you have fast convergence of SGD on weirdly large networks. But it's clear that the reality is somewhere in the middle of these two theorems, and that's where things get harder. So in so to give a feel of what it can look like, even consider a single ReLU gate. So you can write down the subdifferential descent on a single ReLU gate. What you see on the screen here writes that down, loss function and the descent. And we can ask, what does this stochastic process converge to? If we look at the sequence of weights this update is doing, even on the simplest neural net out there, we don't know. This is still open. So unless we make very strong assumptions about what the Y is. If you make very strong assumptions about what the structure Y is, then I can tell you something about where the sequence of iterates is converging. But otherwise, even for the simplest neural net, understanding subdifferential descent is outside the scope of all-known theory. So proof of trainability remains open in pretty much everything real world at this point. So in 2020, we sort of started asking this question more carefully. Okay, are there examples where we can write proofs of convergence where the neural net is finitely large, data is not realizable, and the algorithm has to behave somewhat like a stochastic gradient descent? And we were able to come up with some examples. Let me show one such example. So one example we did was to understand the convergence on a single ReLU gate, where I'm allowing for a adversarial, probabilistic, and bounded additive distortion to the true labels. So alpha ti are Bernoulli random variables, and psi ti are bounded numbers. So some adversary sort of making perturbations to the actual labels generated from a neural net of weight W star, and it's making them probabilistically and additively. And I want to say, given this kind of an adversarial attack that is going on the training data during the run of the algorithm, can I still get very close to W star? This is a question we want to ask. This is a very standard way of framing a data poisoning resistance question. And the issue is that we don't know if stochastic gradient descent can do anything here. There's no proof available at this point of stochastic gradient descent being converging anywhere near W star in such a general setup. So we analyze this for a stochastic gradient-like algorithm, but not exactly. But we slightly modified where the indicator is. And this is where the magic lies. indicators in the usual stochastic gradient descent are on the current weights. But we said, let's put the indicator on the labels, not on the weights. If you do this small shift in the definition of the indicator, this stochastic process has a provable convergence. I can guarantee how close it will get to W star, the true weights, in how much time. I can give this time estimates now for this stochastic process. And that's, I think, an important insight, that an algorithm which is real life successful can be slightly modified so that suddenly I have convergence guarantees for it. And what is maybe more surprising is that when you look at the plots of this algorithm and compare it against actual SGD of the same training data, you see that the two plots are nearly identical. So here I'm looking at the trajectory of the algorithm as plotted in terms of distance to the original global minima for different values of the distortion I put in. So the blue is where the distortion is lowest, brown is where the distortion is the largest. And as the distortion increases, my ability to get close to the true global minima keeps falling as expected. But what is interesting is that true SGD, which is the right-hand plot, and my modified SGD, which is the left-hand plot, are nearly identical. This is kind of, I think, an important message here. And this also happens in the probability of attack way of thinking. Blue is here, again, the blue is when there is no attack happening, and a pink is when there is an attack happening. And there is a graceful degradation. And again, SGD on the right and the modified SGD on the left have nearly identical plots. While the left-hand diagram is provable, while the right-hand diagram is not provable. And this, I think, is probably an important philosophy to going forward, that real-life algorithms where proofs don't work, maybe it's possible to tweak them slightly so that proofs work without damaging the trajectory too much. And I believe this is an important direction of research going ahead, for which we have given a few examples already here. Okay, so now let me take a different turn in the talk. So far I have been talking about tracking down the weights behavior during neural training, which is sort of like taking a microscopic view of neural networks. Like, let me track down what the weights are changing, how the weights are changing during neural training. Another view can be to be inspired by how physicists have thought of hundreds of years to say, okay, let's not track at the atomic level, let's track at the phenomenological level. Like what happens in Navier-Stokes equations. You don't track every water molecule's behavior, but you can model the large scale behavior of fluids by looking at essentially three parameters: pressure density, velocity, and viscosity. And we want to ask, is it possible to do the same for neural networks? That is it possible to abstract out a neural net's properties into some phenomenological properties which will be enough to give you a large scale model, which is accurate enough in its predictive power, while I do not have to track every trillion parameters out there, which is actually changing during the day. And this is a philosophy I want to investigate a little bit more. And the question is, what are such universal properties? Are there such universal properties which hold across multiple networks? And which can give such a phenomenological handle into deep learning? There was one interesting guess of such a parameter in 2020 by Weijie Su and Hangfeng He, who essentially said this, that for any function class f, this doesn't even have to be neural, it is a very general definition. Consider the algorithm as going through a sequence of weight updates, which are like W1, W2, W3, and ... And this algorithm could be anything out there, in whatever complicated way you're doing it. But I'm going to insert into the algorithm a new probe, which is going to say that when the weight of the neural network is WT, let me make a fictitious update to WT plus of X, which is as if I did a stochastic gradient update using the sample point X, Y. And then let me ask, at WT, if I did this fictitious update, how much would my prediction change at a new point X prime as compared to the change in prediction at the sampled point X? And I'm going to take the ratio.
Excuse me, where's the Navier-Stokes come in here? I'm confused.
Oh, Navier-Stokes was just an analogy that we need to find large scale behavior properties. This has nothing to do with Navier-Stokes in particular. This definition has nothing to do with Navier-Stokes, but it's a philosophical motivation that I want to look at large scale behavior, which is universal across multiple nets. And
what's the relation? I didn't catch the relation.
It's a philosophical relation. It's not like a mathematical relation. I'm saying it's a philosophical viewpoint I want to motivate using that.
What's the philosophical point of what's the philosophical connection?
The philosophical connection is I want to come up with a quantity which is universal across the nets. Like across multiple training data, multiple algorithms, is there any property which is universally true? And then probably it has a simpler model of this behavior than actually tracking down the weights. This is the question I want to ask. Is it possible to come up with such a quantity for neural training?
The answer is no. That's what Einstein thought also before he died, and the answer is no. We know that the answer is no. But anyway,
in deep learning, I think the answer is yes. So in deep learning, I believe there are such quantities.
Okay.
And so here is an example that we have been chasing down, the definition of SREL. So now this 2-point function that you see here on the screen is well defined for any training process. And we did an investigation of, after these people give the definition in 2020, we ran a lot of experiments over the last 6-7 months to come up with some universal observations that if you train feed-forward nets on any non-realizable data, random initialization and without regularization, then two things seem to hold pretty universally. One is that if you fix your testing point x prime and you change your sampling point x farther and farther away from x prime, then your local elasticity function actually decreases, which essentially says that the influence of the sampling point is local. It's local always. No matter how you do the training, what net, what data, it's a local influence. You cannot influence the entire function's behaviors. You cannot influence predictions at faraway points from the sampling point. Sampling point changes predictions only near its neighborhood, not far away. This is the property we seem to see hold across lots of experiments. Second is, if you fix the 2 points, the sampling point and the testing point, does this influence propagation have a time dynamics which is universal? It seems to be yes. It has two-phase behavior. The first phase is that it is rapidly increasing. It's small and rapidly increasing. And the late time, it sort of stabilizes in a somewhat large time. So there is this phase transition kind of a behavior between any 2 points if you fix. It rapidly rises initially and then sort of stabilizes into a large value. It can sometimes be mildly increasing also, but some large value it stabilizes. And this correlates to the risk function actually. So it's a local probe which actually probes the global property. The part when the elasticity function rises fast is precisely the point where the loss functions fall fast. So the time derivatives of the loss function, the elasticity function seem to have a correlation. And when the elasticity function stabilizes, the loss function also stabilizes. This is again a property we seem to see holds over multiple experiments. So to summarize these experiments, we say that there are two properties of neural training which probably hold universally. One is locality. Neural dynamics is local. You influence, your sample point influences only in its neighborhood and not far away. Second, which is completely unlike linear functions. Linear functions make global changes continuously. Any sample point, you do linear regression, the whole function changes, essentially. You can make arbitrary changes elsewhere. These are non-linear in a very special way that make only local changes. Often we give the analogy of plasticity. It's like plasticine modeling. As if you're making a statue out of pressing plasticine. You make small dents and you get a statue out. So that's how neural training happens. And the other is the phase behavior. There are distinct two phases of neural training. One phase when elasticity function is rapidly rising, and a second late time phase when it is asymptotically stable at a large value. And there is a classification version of this two-phase behavior also, but it's a more complicated story which we are currently developing, and I'm not talking about it here immediately. There is a classification version of this conclusion, which gets a little more complicated than this. The question is, what kind of function spaces can we write down on which this is maybe somewhat reproducible mathematically? So we come up with a function class to do such an analysis, what I call the higher order NTK functions. Let me define them. So these are the class of functions I'm going to focus on to build a mathematical model for elasticity. So what you see on the screen is basically a sum of alpha x, which is a function, alpha some function, plus a sum over inner products, where betas are like feature vectors. And inner product of beta rx with wr to the power of d. So wr's are vectors, which is the parameters I'm training over. So there are w such wr vectors. And wr to the power of d means Hadamard power. The wr vector taken dth Hadamard power. And inner product with the feature vector beta rx. So this class of functions that you see, it's nonlinear, but it's degree d homogeneous in weights. Sorry, it's not. I want to say it's like, yeah, it's not degree d homogeneous unless alpha x is 0. And it is a polynomial. That's very important to keep in mind. So where do these function classes come from? One might ask for some motivation about it. The motivation is basically this. Consider a special case when d equal to 1 and beta x is the gradient of the neural net at initialization of training, and alpha x is the value of the function initialization minus the inner product of the initial weight and the derivative of the initial weight. If you look at this special case of this function class, it reduces to a particular function class, which is called the NTK class. What is the NTK class? We believe at this point the conjecture that if you take any sequence of neural nets at a fixed depth but increasing size, then this sequence of functions converges asymptotically to a particular class of functions, which is this special case. For this D, this alpha, and this beta. And this is called the NTK class. So this is a belief at this point, which is pretty strongly held in the community. And it has explicit proofs at various levels of rigor for various special cases. And we probably believe that it more or less holds universally. That any sequence of neural nets of increasing size at a fixed step asymptotically converges to the NTK class. But the problem is this. NTK class is D equal to 1. So this will make the function linear. If you go back to my definition of elasticity, you will see that squared loss on a linear function will lead you to constant elasticity. But that is not true in real-world experiments. In real-world experiments, elasticity has non-trivial time dynamics. So you asymptotic limit of large nets distinctly differs from how actual neural nets behave when seen through the lens of elasticity. So which tells us that we should not be writing proofs about asymptotically large nets, because there's a clear phenomenological difference between how asymptotic large nets behave and real-world nets behave. And one way to move away from asymptotically large net is to say, okay, let me ad hoc define a power D. And say, okay, let me take a power D and let me see if I can reproduce still some neural property. Well, I know that D equal to 1 is the NTK limit. And there's a connection to some recent one recent paper had come out, not recent actually, but okay, 1.5 years ago pretty much, about showing something called they also called it higher order NTK functions. And this is sort of related to that philosophy, but not exactly so. It's sort of slightly simplified than what they call higher order NTK, but it's a special case of that. In a sense, it's a special case. So we analyze this. We analyze this function class by looking at the gradient flow on it. So I can write down the squared loss for this function class, write down the gradient flow. It's a coupled system of ODE. And it's a very complicated system of ODE, which a priori I don't know how to analyze. But I can make assumptions about the distribution. So I make some diagonalizing assumptions about the distribution, which is instantiable. I can write down distributions and explicit betas for which this orthogonality properties are true. I make some finite moment assumptions, some orthogonality assumptions across the distribution for the betas, so that I can decouple the system of ODEs. Once I can decouple the system of ODEs, I can exactly solve the ODEs. I can write down the closed form solution, and then I can write down the SRL on the solution of the ODEs explicitly in a closed form formula, as you see on the screen. This is an explicit expression for the elasticity function on my function class in a special case where I can do some decoupling. And it's not clear to me, I don't know if it's obvious to people in the audience as to what the shape of this function is. It was not obvious to me what the shape of this function is till I plotted it. So I went ahead and plot this function. And here is the plot. I see that I can see approximately the same two-phase behavior come back. There is a part where it's initially rising, and asymptotically there is stability. And it is internally consistent, because on the same function class, if I run SGD, then I get the red plot. So the SGD behavior of stochastic of elasticity on this function class is entirely consistent, almost identical, the gradient flows behavior of elasticity on the same function class. So it's internally consistent, and it gets a part of the neural behavior correct, at least some part of the important neural behavior correct. That there is a rising part and there is a stabilization part. And you can, some more data you can try to get it, see again and again this feature comes back. So this leads us to the conjecture that maybe elasticity function in the limit of this eta parameter going to 0, evaluated on solutions of gradient flow, is in fact the true behavior, is very close to the true behavior of the elasticity function on SGD. So this is a conjecture at this point, which we cannot prove. Like evaluating the elasticity function on SGD is a very technically complicated thing at this point. Like we have no idea how to do that, but we can evaluate gradient flows. And that leads us to this conjecture that this is internally consistent and it's a good model for neural behavior. So here is a chance that maybe there is a way to write down ODEs for certain abstracted out parameters of neural training, which reproduce neural behavior. So this leads me to the end of the talk, where I want to end with a set of open questions that I'm thinking about. One is to say, let me look at alternatives to SRL. So SRL is a very challenging function to control. I do not know how to write the SRL exactly for SGD or even a linear function. If you try writing it, you will get into immediate mathematical problems there. So it's possible that this elasticity intuition can be captured by simpler alternatives to SRL, and I cannot rule it out at this point. So I think it's an important direction to come up with simpler alternatives to the elasticity function, which capture the same 2-point influence behavior, but is mathematically easier to handle. What is such a definition? Is I think an interesting question. Second is, I want to talk about this ODE system as a whole. So I've given you hopefully some evidence as to why this ODE system is captures some of the neural behavior correctly, but we have analyzed it only in a very specialized limit where certain decouplings happen. Maybe if somebody could analyze the ODE system more generally, it would reveal more accurate neural modeling. In particular, we want to have a prescription which tells us how to choose the alpha and the beta function given a neural network. And this mechanism still doesn't exist. And there's this paper by Bai and Lee from 1910, which sort of gave another motivation for certain quadratic functions, which they had an argument of why the model neural behavior. So this Bai and Lee model of certain quadratic functions being good neural models could be another test case for the same philosophy. So why do you have to look at just maybe my quadratic functions where I am doing the modeling may not be the most accurate function class where the modeling can be done. Maybe the Bai-Lee quadratic functions are better models in this of elasticity than my quadratic functions. And there's a possibility that I would like to explore further. The problem with the Bai-Lee model currently is that it's complicated to integrate the ODE in their model. As far as I've thought about it, I could show you explicit gradient flow solutions on my model and show that it's internally consistent. This argument in the Bai-Lee model is currently difficult because the coupling is so complicated there. It's quadratic, but the internal coupling is so much more there that it's not easy to decouple and get a close from yet. So I think it's an important direction to push ahead to reproduce my story on the Bai-Lee model. Both are quadratic, so maybe the whole picture goes through, maybe it's more accurate, worth an investigation. And why not higher power? Why just stop at quadratic? There's a systematic way to go to cubic, quartic, and higher degree polynomials, which are systematically neural approximators. So Bai-Lee had shown a way to get these polynomials. So maybe one can push even ahead, at least numerically. Okay, test it at higher and higher degrees, whether SRL continues to get more and more accurate models. Okay, that's one direction of study. The third is in general gradient flows. So this is the particular kind of gradient flow that we are focusing on, where the time derivative of the weight is negative of the partial derivative of the risk. To the best of my knowledge, as far as I've searched the mathematical literature, I haven't found too many theorems about this gradient flow. Maybe they exist and I haven't found, but at least I haven't found them as far as I've searched. I was to understanding this particular class of gradient flows. Like, when do they actually minimize the risk? Is there a general theorem can be found of when do these gradient flows are integrable? When do these asymptotically go to the global minimum of the risk, and particularly for non-smooth, non-convex functions? So that's, I think, is an independent investigation that is interesting, I think, understanding this particular class of gradient flows. The last question I want to come to is, okay, I did not put it in the slides here, is that I've recently been thinking about, let me just say it verbally, is that if you take any neural network, you can compose it again and again. Like if you FW is a neural network and you compose it again and again, you can ask for a fixed point of the neural network infinitely after infinite compositions. And there has been an interesting line of research in recent times showing that infinite composed neural networks have a fixed point. And when they have a fixed point, that fixed point can be trained. You can train the weights so that the fixed point has certain nice properties. And this particular training seems to succeed. And they seem to essentially do better compressed sensing than actual compressed sensing. And this philosophy is what is sometimes called deep equilibrium models. I'm very interested in deep equilibrium models, and I've recently written a funding proposal for that with Professor Rebecca Willett in Chicago. We have written a whole detailed funding proposal on these deep equilibrium models. So I think that's an important direction, given everything I've already said about sparse coding in the beginning of the talk. If sparse coding is well done by neural networks, maybe the next step is to understand compressed sensing. And compressed sensing, we believe that infinite neural networks can be defined, which will do better compressed sensing than the current techniques are available. So that's the last thing I wanted to verbally discuss. It's not in the slides. And I would want to end the talk here by giving a list of references. So the first reference to this 2016 paper of ours, you can look into it for more details on function space theorems. Lots of depth hierarchy theorems are there. Approximation hardness theorems are there, which I did not get into here. Also, we have proven theorems about complexity of neural functions, like what makes one neural function more complex than the other? Is there a way to measure complexity? And we showed a way of measuring it, and in this paper, we show how we can construct highly complex neural functions measured in our way. And that has spurred a lot of research in recent times. And various groups have taken forward this research of ours and constructed more and more complex functions using that technique. So this paper 17, you can get more details on the sparse coding proof. These two papers are 2005. These two 2020 papers these two papers together give many more examples of this kind of non-gradient neural algorithms, where I show that you can take the gradient descent algorithm, slightly change it, and make it provable, while the actual SGD is still not provable. And I believe this is an important philosophy going forward. We have currently done it for SGD. Many examples of SGD we have been able to do it. Maybe the next step is to try it on RMS proper atom. Take the RMS proper atom, slightly modify it so that it becomes provable, but be able to show that its trajectory is identical. So we have done this for SGD in many cases in these two papers. And this is the end of my talk, and I'm happy to take more questions.
Okay, thank you very much, Anirbit, for your great presentation. Is there any questions for him?
Hi, Anirbit. This is Jen
Yes.
from Crunch Group. Yeah. Thank you for the very nice talk. So I have a question that I remember you said, like for the gradient flow. So I mean the gradient dynamics of the neural networks. You say that you have two properties like the locality and the two-phase training. And
Yes.
Yeah, as to locality, I'm wondering like. So this is for like general neural networks, but if you have some specific structures in the neural network, for example, like the physics-informed neural network, like I think that like the locality will become less evident. And do we have some kind of global, I mean, like a global, some global properties for
So the questions I don't have you checked. So the questions I would say check the locality property. I would say do the experiment of computing the SRL function on your favorite neural network and see if you can reproduce this plot essentially, this left-hand plot. So this left-hand plot is what I'm calling as the plot that demonstrates the locality. So if you show me a neural experiment where this is violated, then that's interesting. In the sense, and as I keep saying, I need two important properties for this plot to be reproducible. One is starting from random initialization and not using regularization. So if you can show an example of a neural net which is randomly initialized for training and it does not use regularization and it violates locality, that would be an interesting example. Think of this. I have not yet seen. So if you have an idea of a neural net where this triangle breaks, I would be delighted to investigate that example further. We don't know at this point of a mechanism by which I can just look at a neural net and a training and say that, yeah, this will have the locality property or not. We don't have a litmus test of that kind yet.
Yeah, okay, thank you. That makes sense.
And is there any other questions for Anirbit?
Youngjon, do you have any questions? Youngjon Shin?
Hi.
Hi.
Thanks for a nice talk. I'm wondering, because what I found is that empirically, it is rather might be a comment or question, but gradient descent seemingly doesn't really working properly in real practical problems. For example, if you just use pure gradient descent, small learning rate, when I run it on computer, it doesn't seem converge, and I don't really see real practitioners use gradient descent.
I
mean pure gradient descent. So
yeah, I guess you want do you want to say that Adam performs better than SGD?
Right. So I'm wondering how those results can provide some insight or some practical guidance on, or what kind of the action should we take? For example, like neurotangent kernel, seemingly and theoretically is pleasant thing. I mean, we can prove something is a relation to the kernel, but in practice, when I use a two-layer neural network with a lots of layers, doesn't really perform very well. And also there is a paper by the Princeton group, and also showing and indicating that neurotangent kernel seemingly doesn't train well because it doesn't travel a lot, so it doesn't really learning feature rather than So, given those informations, I'm wondering what I'm maybe asking for your perspective, maybe wondering like those similar results can extend to further to, like, for example, mean field theory regime, or
okay, so let me make let me put the comment in two parts. So I indicated about the Adam story here in this slide, where I said that you can use a general VT is what is used. General algorithms look like this slide I had. Yeah, where I said that in general, it will look like some VT, and VT is a complicated function of the previous gradient seen. So that's why I sort of hit the Adam story here. I would strongly encourage you to read my paper on Adam. I believe the first proof of convergence of Adam was my group. So we gave the first proof of convergence of the Adam algorithm. We also gave the first proof of convergence of the RMS prop algorithm. So currently we have a project under the works where we are trying to improve those proofs. So I think proving Adam and RMS prop is a very fundamental research question in my mind, because they work the best and they are seeing something about the neural structure which SGD does not see. So I have a whole program going on about proving Adam. So I have written a paper. I would strongly encourage you to read it and see if you can improve the result there. Stochastic Adam is still unprovable. So it's a very hard challenge to prove any of those algorithms. So I have tried a lot. I have some results, but we are still very far from, I would say, the ideal result that we want of Adam converging on a neural network. Like that has not yet happened. So I totally agree with Adam being an important question, and I have invested a lot of time into that. I can share more details on the 2 or 3 drafts that we have written on that story. But then the point is, we also want to ask questions about neural dynamics which do not depend on how you're training. That is where the elasticity story comes into picture. The elasticity properties that I was talking about here is kind of trying to get there. That these properties that you are seeing here do not depend on whether the training is RMS prop or Adam. So there are 2 parts to this philosophy. Yes, I want to prove theorems about Adam. I have invested enormous energy into proving Adam. I would be happy to, you can see my paper on archive on it and my more newer drafts which are not yet available. I can show them to you. And improving them is a very hard problem. But on the other hand, we also want to prove theorems about neural dynamics which do not depend on the algorithm. So I would say there are 2 directions of research, both are interesting. And about the NTK, yes, I totally agree that NTK is not a real model of neural networks. And that's exactly what this plot is telling you. This plot you see on the screen, right-hand side, is telling you why NTK is not a good model. Because if you do squared loss linear function, NTK, the limit point is a linear function. So if you do squared loss linear function, SREL would become a constant. It's just easy to prove from the definition. But we know in real life neural nets, SREL is not a constant. It has dynamic. It has a rising phase, and asymptotically, it doesn't really become a constant. It has a slight increase often. So this plot, in fact, this right-hand side plot on your screen exactly gives the message that NTK is not the real world net. So I want to get away from NTK, but you want to preserve the analytic control that NTK gives. So how do you systematically get away from NTK while preserving the analytic control of NTK? This is the important question. And that has started to be addressed in at least one paper I know of, which is the Bailey framework. The Bailey framework gives you a way to perturbatively get away from the NTK. So, and it is sort of interesting that the Bailey framework gets to a function which sort of has the same flavor as on which I'm doing elasticity. So that is why I said maybe the next step is to do the elasticity analysis on the Bailey approximates. So that's, I think, a very important direction of research.
Can I ask you some follow-up question? Thank you for a nice answer. Speaking of the Adam conversions.
Yes.
Sorry, I haven't read your paper yet, but as far as I know, Adam, do you prove Adam converge?
The proof that I have currently is that on smooth functions, whether or not they are convex, Adam without stochasticity can get to criticality. That is what the proof I can, and I can give a time bound. I can give you, if you want the gradients to be epsilon, I can tell you how much. I can give an upper bound on the time Adam will take to get to epsilon small gradients.
Oh, I see.
That's the proof I can give at this point. What I cannot give, which is still an open question, is can you prove the same theorem with stochastic gradients?
I know that there is a paper that the people proposed a continuum version of Adam, and also under certain conditions of the hyperparameter beta 1 and beta 2 converges to 1, properly scaling that converges to the solution, the stationary point. And
yeah, so I think you're.
But what I found in the in practical situation, we never see Adam converge stably. So I'm wondering, do you assuming something like diminishing something?
No,
I'm not sure. I better to check your paper. Maybe might be send through the chat what reference I can look up. Maybe
so there is a distinct gap between theory and experiment of Adam, because when you say Adam does not converge in experiments, you are looking at probably at neural experiments.
Right, and also others. Yeah, there are many examples that Adam does not converge. I mean, okay, I in computer time I can run it at most like 1 million iteration. Then we never know, like it converges like trillion iteration. Then we never know. So that all I can say is that within 1 million iteration, it seemingly doesn't converge. So there might be biased statement for what I just said, but just
I would say the most important point is that these experiments are running on neural networks, and neural networks are non-smooth functions. And
neural network are C infinity if you use the tanh or hyper C infinity function.
Well, then it's a different question. But I am most familiar with Adam on ReLU networks, where non-smoothness is a big deal. And as far as I understand, non-smoothness of the neural network is the fundamental property of neural network. If you make the neural network smooth, there's a distinct damage done to neural net's ability. So Adam in non-smooth functions is where no theory exists. I am not aware of a single theorem out there, even a shred of a lemma about Adam in non-smooth functions. So I would say we have no understanding of what Adam does in non-smooth functions. We know of standard theorems about how gradient descent behaves with non-smooth functions. We have standard theorems about how stochastic gradient descent does in non-smooth functions. We have some understanding, but Adam in non-smooth functions is absolute dark. We have no theory I know of even goes anywhere close there. So, extrapolating intuitions from smooth function proofs to non-smooth function proofs is, I think, dangerous. So I mean, I'm not going to ever claim that my theorem about smooth functions tells anything about Adam on neural network where smoothness is gone. So smoothness is a very, very difficult barrier to crack. So like I was talking of this theorem, like I gave the reference to this theorem here. This is sort of the state of the art at this point, this paper, 1912-07146. So this paper is, as far as I know of, the state of the art theorem about stochastic gradient descent for non-smooth functions. So if somebody can reproduce the result of 1912-07146 for Adam, that would be, in my opinion, a breakthrough result. But this is extremely complicated proof about what is stochastic gradient descent for non-smooth functions. And going anywhere close to this result for, forget Adam, even RMS prof is not clear. So non-smoothness is a very difficult barrier. Like this kind of proofs for for smooth functions, this analogous result for smooth functions barely takes 4 pages. It's a 4-page proof. This what they are proving for smooth functions is a 4-page proof. Once you remove smoothness, it's a 50-page paper. So smoothness is like a barrier, is a huge technical barrier. So yeah, Adam on non-smooth functions, all bets are off. What the guarantees are.
I have a question. We saw in your references you have some reference to the work of Poggio. So can you?
Which reference? Not in this slide.
I think the one with the BU.
Yeah, Sang Peter Chin at BU.
Yeah, and Akshay. I think Akshay. I think Akshay is a.
Yeah, Akshay is a postdoc with Poggio now.
Yeah, he's postdoc with Poggio. Okay, so I was wondering if you refer to, because in Poggio's group, they are looking at gradient flows and they're looking at the effect of initialization. And so Are you familiar with that work?
I am familiar with gradient, I'm familiar with some works on initialization effects, scale of initialization effect, but I'm not familiar with Professor Poggio's work on the same specifically.
Okay, okay.
I'm familiar with some other works about the scale of initialization question.
Okay.
Is there any other questions for Anirbit? If not, then let's thank Anirbit for this great presentation. Yeah, thank you very much, Anirbit.
Thank you.
So now let's welcome our second speaker, who is Ankit Shrivastava. Hi, can you turn on your video?
So should I just stop
Ankit?
sharing the screen, I guess?
Yes, please. Thank you. Hi, Ankit. Okay, great.
Can you hear me?
Yeah, I can hear you. So yeah, let me briefly introduce him. So Ankit Shrivastava is currently a PhD student at Civil Engineering Department at CMU, and he's now working with Professor Han-Yon No and Professor Kaushik Daniel. His work is on analyzing factors responsible for a high stress inside heterogeneous materials using data science. He completed the master's degree in computational science from the Indian Institute of Science and the bachelor's degree in civil engineering from the Indian Institute of Technology. Yeah. So today, Ankit will give us a presentation with the title Predicting High Stress Regions in Microstructure Using Deep Learning. So Ankit, you can start your presentation. Yeah.
Hi, good afternoon, everyone, and thank you, Andre, for giving the detailed introduction. And thanks for inviting me for the talk. So I have been working on this problems with my professor, Hyung No. She's from currently from Stanford University. Earlier, she was from Carnegie Mellon, and my co-advisor, Professor Kaushik Dayal from Carnegie Mellon. So today my focus will be just on the prediction mainly, and not on the complete investigator. So, so what my focus is on understanding mainly two kind of materials. One is this granular system, and the other is this microstructure. So and the goal is same. That is that can we predict the can we predict these high stresses inside the microstructure, and can we analyze what factors are affecting these high stresses? A similar goal is here that can we, from given the granular system properties, can we know what factors are actually causing these high stress force chains? So for this presentation, I'm mainly focusing on the microstructure part, and if some time is available, then I would like to discuss about my ongoing work on granular system. So before moving forward, I just want to present an outline of my work on microstructure in this one slide, and this is what I will be discussing. So for this presentation, I'm not going into very much detail of this encoder decoder model. I'm assuming that our audience here might know much about basic components of like models such as autoencoder, where you have this convolutional and max pool layer. My focus mainly is here to on this work was to understand how good these models are when we apply them in problems such as microstructure, and how intuitively can we understand whether those models are working or not, and where these models are failing. That's what. So for those who don't know what microstructure is, I will explain this in the next slide. But for now, you can just consider it as a non-homogeneous material on which we apply an external load, and we obtain some stresses inside them. So my whole complete work is divided into this three parts. First is the model design. So where we use this deep learning based encoder decoder model to predict the stresses, and then from there we try to characterize these high stress regions, also called hotspots. Then once we train the model, we actually try to evaluate by some different metrics, and we came up with some of our own intuitive metrics to understand what features of these hotspots are better. And we also try to evaluate that for what kind of samples it's not working. And like this kind of information will be very good if we want to improve our model and the application of this field. Then the third part, and this is the most important goal for my thesis work also, that can we, given this microstructure and hotspots, can we use this encoder decoder to interpret something, some statistical relations or some relations? Can we answer some of our questions? And this is what my focus has been on. So for those who don't know what microstructure is, I will start with the basics. So if we take any material and we observe them at a micro scale, so we see this non-homogeneous structure inside them. And we call this complete thing as a microstructure. And when we apply external load, what we will see is that there are like non-uniform stresses and developed inside them. So in this microstructure, we have this grains and the grain boundary as one of the structures. And in this, each grain is actually a crystal, which represents the arrangement of these atoms in particular orientation or particular fashion. So what we see here is that there are some high stresses that are created. And in the field of material science, they are usually referred to as stress hotspots. So what it has been observed by the experiment, and it's been suggested by the various papers, that these hotspots tend to initiate the failure mechanism inside the material. So for example, this is like one of the explanation by the paper with in the following paper. So what happened is that if you look at this hotspots, if under the applied strain, and if you keep on increasing the strain, there will be a void that will start, and then this void will grow and eventually lead to a crack at intergranular phases. So this essentially that's why it is important to know where these hotspots are being created and what factors are actually causing them. So what as of now, what we know is that these hotspots tend to lie near these grain boundaries and junctions point. So one of the explanation is that since these grains consist of this anisotropic crystals, all these grains, when we apply a load, these crystals will tend to extend and stretch in different direction or resist in different direction. And this different direction resistance will eventually lead to creation of some of these high stresses. This we can say a similar example where like this is a video that I found. So what we see here is that the grain boundary attack is being initiated inside the material, and like this is that's what we that's why this is very important to understand that can this what kind of these features are actually causing this high stresses. However, what we know is that in these images, these hotspots are really sparse. So they are like not at every junction points or at every grain boundary you will see these high hotspots. So there has to be like some features in the microstructure which are actually creating them. But and that's the main question, that we want to know what features of this microstructure are causing them. So one of the major research question arises is that we don't know, we don't see hotspot at every junctions. So what combination of these features are actually causing them? So for example, why the hotspots are here but not at here? And we don't have any analytical relationship or any statistical relationship to understand this thing. The second major question is this long range interaction. That is this hotspot being created only with this region, or is the hotspot being created with some large region? How are they playing the role? And can we characterize this kind of interaction? That is the long range interaction. So answer to this kind of question can be very beneficial if we want to design the high strength material. And what I'm trying to look for the answers using data science. So although there are like numerical schemes such as like finite element, Fourier space, where we can actually simulate the material and observe the stresses, And then we can use some image segmentation techniques to observe these hotspots. These techniques actually doesn't help in interpreting that what hotspots are, like what factors are causing these hotspots. So for example, like even if we have the large number of even if we generate large number of samples from using this finite element, and if we are trying to observe manually, it will be very difficult. And if we are trying to model some kind of model using some look some for the statistics, it might have some bias. So what we need is a kind of statistical model which automatically captures these relations and then try to tell us. The other advantage, as you guys might know, is that machine learning tends to be very computationally efficient as compared to this model. So as compared to this numerical scheme. So if we want to use them for the on-site design of materials, then it is very useful. So what we can do,
Ankit?
Yeah.
Hi, this is Mellon.
Yeah.
I have a quick question. So how do you define a hotspot?
Yeah, that's a good question.
Based on the stress image.
Yeah, so that's a good question. So actually, I will actually tell you how I'm defining the hotspot. So there is no standard definition for this hotspot. What we know is that we have to define these clusters, but there is no existing different people use different definition for this hotspot. And we came up with our own definition based on intuition.
All right, thank you.
Yeah, so I will actually explain in later that what criteria I've been using and how we are actually characterizing these hotspots. That's what I will explain. Okay, so what our plan is that we generate the data from these numerical schemes, and in our case we are using this Fourier-based schemes, and we simulate the model, generate the data, and then we try to use some kind of statistical model for this. So just before going forward, I just want to explain what kind of data set we are dealing with. So, and under what conditions. So we have this microstructure image, which is a synthetic image generated using a Dream 3D software. And these microstructure are like single phase and cubic crystals. And it is actually a 3D crystal in a 2D domain. And that's why it has a 3-channel images, where each actually channel is representing an Euler angle in particular direction. And this Euler angle or the orientation of the crystal are represented in the Bungee convention. So what we do is, like, we take this microstructure, we apply a load, strain, in the direction perpendicular to this surface, and we solve a linear elasticity equation, and then we obtain these von Mises stresses. So what we actually started, when we started this problem, we started with simple statistical model such as regression, where we would give some regions around the hotspots as one of the features, and we will ask the model to learn the features. Then we also tried to use the CNN model, where we would give it a complete image, and then we would ask them to predict some peak stresses. However, both these models were not working, and what they were highly inaccurate. And so we realized that we are facing with this following major problem. The first is that the images are very high dimensional. So we need a large number of samples to train the regression models. And then there's a complex spatial correlation between this two images. So there would be some area would be related to this some area, and even this area might be affecting the stresses at this point itself. So there's a lot of complexity, and that we were not able to properly provide in the regression models. So the main problem main problem is that we exactly don't know what area of this microstructure are correlated. Is it like the complete image is correlated to each other, or is it like only certain regions of this microstructure and which are actually related to each other, that is what we don't know. So this is one of the long range interaction problem. And we hope that the model that we are using, it might be able to tell us something about that.
How many voxels do you use in your input image?
So this is like for 128 by 128. And this was also, so initially we tried with 128 by 128, but I will actually explain that we had to reduce its dimension and work on approximate stresses for some reason. Did the answer make it clear? Or?
Yeah, thank you.
Okay.
We'll take a look.
So yeah, so our goal was to find this local spatial relationship among them. So like to solve this problem, we have to think about the image to image mapping. And it turns out that there are models such as convolutional autoencoders that have been used in material science for microstructure segmentation or reconstruction. So in our case, we can use similar models, but instead of mapping from microstructure to microstructure, we are mapping from microstructure to a stress image. And that's why we call it an encoder-decoder model, not an autoencoder. So what we do is, like, it has some basic components, and as the name suggests, it has encoder and decoder. And what we expect for the encoder is to capture the features of the microstructure using the filters such as convolution and max pool, and then map it into compressed information, and then we can use the decoder to map use that compressed information into stress map. So so in the there are like multiple there is like tuning involved where we use different layers, but we just work with this convolution and max pool and encoder, and then there is this in that decoder we just work on transpose convolution. So like there might be a question that you may ask, that why we are actually, this model looks very simple, and that why we could have used some complicated architecture, or like we could have used GANs. Like these GANs have been asked many times to me, and like they might perform better than this. But since our goal was to like analyze what features are actually affecting this input and output, like what is the, and we wanted to interpret them, we decided not to go with very complex model. We decided like, let's keep it simple. Can we observe with this simple architecture or not? And that's what we are trying to do right now.
Ankit, can I ask a question?
Yeah, sure.
So are you looking at, I'm Kaichi from PNNL. Are you looking at specific loading pattern? Because the stress field not only depends on the microstructure, but also the boundary condition, the loading pattern you apply on the.
So right now, my complete data is focused only on one loading pattern. So we have fixed everything. We have fixed the boundary condition. We have fixed the external load that we are applied. And we are just, whatever the relation that we are observing is based on only, is constant under those assumptions. Like what my goal is that if we can observe something with this encoder decoder, and like we can interpret this, then maybe we can try with even different boundary conditions, different loading condition, or even we can move to a plasticity model also.
Because for the traditional reduced order model for microstructure, I saw some literature will use the so-called eigenstrand, because for this linear elasticity problem, only 6 eigenstrand for this kind of microstructure.
Okay.
But you're only looking at single one, right? Just one axial tensile loading.
So let me just rephrase your question. So what you are asking is that, is the applied load the same applied load, or like, can you repeat the question? I'm not sure I followed it.
I just want to check whether you only use one type of traction boundary condition for this model, or
Oh, so okay. So I'm just trying to use only this loading, that is like loading perpendicular to the plane. Like, so
I see.
all of my data is generated with this condition. Like this is fixed, everything. The
Okay.
boundary condition is fixed. My bound.
Okay,
Yeah.
got
So
it.
that's what I was saying. That otherwise we have to provide this information also. And right now we are not interested in that much. We just wanted to see if can we interpret the model or not using this thing, this encoder decoder.
Okay, thank you.
Okay.
Sorry, so the heterogeneity in your material is only due to the crystal structure, yeah?
Yeah, yeah. So it's
So
a
you
single
have a
phase.
material, you have a single material, but the microstructure, so on the grain level is different. Okay.
Yeah, yeah, exactly. Yeah. So we actually try to simplify the problem as much we can. And I'm also working on one case where I'm just using a pure 2D crystal, not a 3D crystal, and because the interpretation is still a little difficult. But yeah. So this is like our approaches, that what we are doing is we are training the this encoder decoder model with the data set generated from the scheme. So I just want to clarify here is that our goal is not to exactly predict the value of stresses. So we are not actually giving, so in our objective function, we are just using mean square loss. We are not providing the information about the boundary condition or stress continuity equation condition. We are not actually giving that. What we want the model to do is we want model to learn the pattern. Like we want to have some model to learn some relationship between these two things, like hotspots and the microstructure feature. That's it. I'm not expecting much more from. So that's why what we do is, like, even if you have one misses test, we actually destroy the original information, we rescale, resize the information, and then we try to understand the relationship. So after this, what we do is, like, okay. So once we try to interpret the, once we train the model, we actually are trying to interpret it by, like, using some different visualization, feature visualization methods. Like I will show one of the results that we have observed, and then the other is this, and we are using this gradient visualization to understand this non-local relationship. So gradient visualization should tell us that if I want to see this hotspot, what regions of this microstructure is causing them. So this similar thing is used in CNN also, where they use this gradient based schemes, like they got guided back propagation and more. We want to use something similar just to observe this kind of relations from this encoder decoder. So I will just explain the details. I'm not going to do very much things. So we have this, like, a simple architecture. We have this. This is my encoder, and then this is my decoder part, and we have trained these images using 8,000 data set. And what we try to do is we try to make sure that all the mics. Okay, I will actually explain that later how we actually decided this 8,000 images. Then we have this simple functions, the ReLU, and I think everyone might know that we use ReLU for, like, computational efficiency and to avoid vanishing gradient problem. And we also use this hyperbolic tangent function, so that because the stress map is very non-linear, so that's hyperbolic tangent function will actually help us in mapping those non-linearity. And the one thing that we did was that we are not using any padding in the our architecture, because we don't want to use any information outside the domain. Otherwise, it will create unnecessary noise, and that was actually reducing this accuracy. So one more thing was that we did not try to use any upsampling layer in the transpose convolution, because we found that transpose convolution was much better as compared to bilinear interpolation or other. And we don't want to use large number of this transpose convolution, because for every interpolation, there is a noise added, which reduces the accuracy of model further. And the other thing that I want to say is that we did not include any neural network like multi-layer perceptron here between this encoder and decoder. And the main reason was that the moment we tried to include this this deep fully connected layer, it was actually destroying the information which was captured by this max pool. So it was not taking all the information properly. And this is like one of the problems being faced in the computer vision also, that sometimes neural network can't capture the complete information of the image. And that's why we use this convolution. We have to use these convolution layers and max pool layers. So just this is just the basic. So we are just using this mean square loss functions. We train it with okay, so this gradient descent scheme, and then we try to predict the ground truth. Then coming up with, so once we train the model, we have this is the prediction of the stress image. And what we want is, since our focus is on investigating these hotspots, there is no standard definition of hotspots yet. So everyone comes with their own definition. We come up with our own definition where we choose these peaks in the images, and we say that, okay, anything above this above a threshold will be your hotspots around that peak. So every peak has your hotspot, and we try to characterize them using this definition. So what we do is, like, we use this different threshold values. So if we are increasing the threshold, the size of the hotspot is decreasing. And the main reason of considering this different threshold was so that we can actually consider the hotspot of different resolution, and we wanted to compare that how these hotspots are actually different from the original stress images. And we study this these details with around only the 3 largest peaks. Like, we are not considering all the peaks, but for now we are just focusing on 3 largest peaks, and we wanted to understand what is the pattern, how the model is behaving with these variations. So once we obtain these hotspots, we need to characterize it. So we decided to come up with some intuitive characterization, such as the location. The first one is location, and the one main reason was, once we are actually, when we start interpreting and analyzing the details, we don't want to we want to make sure that the hotspot is location is correct. Otherwise, we might be focusing on like wrong features. The second thing was the size. So the size represents simply the number of pixels inside the image of the hotspot. And the main reason, the reason for this was that if the size is very large, we might be considering very large regions, and this is what we don't want. And the third thing was the orientation. So we define the orientation by first considering as an equivalent ellipse, and we say that the orientation of this ellipse will be same as the orientation of this hotspot. And this definition is little sensitive, and I will show that this sensitivity was also affecting our analysis in some way. The main reason of considering the orientation was similar, that if we are actually if it's a wrong orientation, we will be considering the wrong pixel, wrong feature of the microstructure while analyzing it. So whole this design was made in keeping in the mind that we want to interpret the model. We just don't want to take the microstructure and predict and just leave it there. That was not our goal. So, in the input, along with this microstructure images, which is like following dimension, we also had to provide this grain boundary information when we were trying it. And this grain boundary is actually calculated using this gradient of Euler angle, norm of gradient of Euler angle. And one of the main reason of providing it was because when we started testing our model with this, the accuracy was little low. And the reason was that it was not capturing, the model was not capturing the grain boundary details. It was just capturing the grains. And it was not properly capturing the these grain boundaries. It was missing many of these grain boundaries. So we had to externally provide the information to it. And at the same time, we wanted to know, tell them about how much the gradient is, how much changes across this, change in Euler angle across this boundary. So this did help us in improving the accuracy a little bit. But the main important part was that it helps in visualizing the features much better. And I will actually show that visualization. The other thing we had to do was that we had this von Mises test, but we had to reduce its dimension because the main reason was that these details are very sharp. And what usually these models we realized eventually is that this model tend to learn this on an average details. They don't focus on very high variation details. So what we had to do, so when we were actually comparing this image and the predicted image, there was large error in the when we were comparing the characteristics. So we had to reduce the image in such a way that we preserve the relative characteristics of these hotspots. At the same time, our prediction, we get some approximate analysis of how what kind of regions it's working well and what kind of regions it's not working well. And it also actually helped in reducing the requirement of large data sets, very large data set for the training. So we started our evaluation. So since the model objective function was mean square error, but we did not use the mean square error as one of our analysis for finding where it's working or where it's not working. Because the mean square error can range from 0 to infinity, and we don't know what is the good or acceptable amount of mean square error value. So the other thing they use this cosine similarity. So cosine similarity is the standard metric used to compare two images, and it ranges from like 0 to 1 right now. And what we see is, and the one value represents a perfectly similar images. So what we see is from this histogram plot that we tested our cosine similarity for this 2000 test sets, and the range is from 0.9 to 0.98, and it is very close to 1. But when we visualized it, we observed that these high stress regions are much better accurately. The pattern of these high stress regions were much better predicted as compared to low stress regions, and that's why it was contributing into this high cosine similarity. And like this is, since our goal is to focus just on this high stress regions as of now, we decided to move forward with this model and just start interpreting on this thing. So one thing we, before doing anything, we wanted to know for what kind of sample it's not working. And like why, if it is failing to predict where it's not, why it's failing. So I just want to say that the way we decided the training set was, we actually had this diameter range, and we actually provided equal, almost same amount of samples, so that there is no bias in the model against any kind of microstructure sample. So what you see here is that average grain diameter, which is like relative to the microstructure size. And we compared here with the cosine similarity. And what we see is that wherever there is like very high, any image which has very large grains or very small grains, the model does not perform very well. Whereas in the medium range, it will perform relatively better. And one of the reasons, the similar observation you can see is here, where you see take this image complete, and you see these regions, and the predictions is almost like very much better as compared to this region, where there is a large grain and the prediction is not good. So one of the reason that we found was that we think it is that since there are not enough features available for the microstructure, so for the encoder decoder model, it was not able to perform very well in this kind of places. Whereas wherever it has a large number of grain boundaries and junctions, it has enough information to predict the variations. So that's why we think that it's not working for the large grain diameter images. The other thing was for the small diameter images. Images. So let's assume that if you have a microstructure where every pixel is your grain, so there will be a lot of variation in the this stresses. So what will happen is that when model is trying to run a filter over it, it will try to use this do this average filtering, right? So it will lose the high variation information and it will just try to extract only low variation details. And that's why this model was fails to work in this kind of thing. So what right now we are working on is we are checking, can we have this kind of filters where the filters are like multi-scale, or the architecture is multi-scale, where we have different kind of filters at same layer and of different size, and can we use them to extract? That's what we are working on right now. So since we know that it's working, so working for these kind of images, and it's not working that well, during the interpretation, we just plan to use images from only these regions and just see how the variations goes in this direction. So apart from this cosine similarity analysis, we also try to see intuitively what characteristics of the hotspots are being predicted much better. And so this was the one of the metric where we use this Euclidean distance and what we see is that so this represents the largest peak, the highest peak inside the image, hotspot around the largest peak. So what we see is that the accuracy decreases if we go down. So this is an interesting observation, and what we feel is this is because of our objective function, where we see where the model is actually prioritizing the high stress values as compared to low stress values, and that's why its location is much better. Then we use this, we were using this orientation metric, and what we see is that in these regions, largest peak error is much lesser as compared to the other two. And we think is that it's the same reason that the model is focusing more on high stresses values rather than low stress value. However, this error is still very large, and so what we are currently working on is analyzing whether this is just because of model, or is it because our metric that we use for the orientation is very sensitive. So for example, if I include a pixel in this direction a little bit, the orientation might change a lot, and we want to actually fix this, and this sensitivity might not have give enough information. So that's we are trying to improve right now. And yeah, and that's why like you see a lot of this discrepancies because of this sensitivity, and that's why I'm not discussing this region right now. And the last thing was this comparing the size. So what we see is that if we increase the threshold value, your hotspot size is decreasing. What it's doing is it's basically focusing on the regions closer to the peak. And what we see is the error is increasing. And the main reason of this error was that the model is not focusing on an average, not focusing on the concentrated details, but on spread out details. So it can be like something like this, where you have this like larger peaks, and then what model will do is model will try to learn something that's why the location might be accurate, but the size of the hotspot might be not. So if I have this kind of hotspot, the difference is very large here as compared to difference here. That's why it's causing the error. The same reason is for the peaks, where we say that, okay, we have this largest peaks, and since the peak will be very higher, the difference will be much larger. So what it tells us is we can't trust on the height, but we can actually trust on the exact shape and the some regions right now and the location. And that's what we see. It actually is not capturing very precise, like minute details of the stresses, but it's trying to capture the overall details of the stresses in the images. So this is like the main summary of this from our analysis. And so one thing is that the model tried to capture the details of high stress regions much better. And since our goal was to focus only on that, that's why it's good enough for us right now. The other thing was that it works only much better for this region of images, and we are not focusing on anything else. And then we know that the location of and we are just focusing on analyzing the highest hotspot around the highest peak, because we know that its accuracy is still much better as compared to other one. And we are like moving forward with that details. So when coming up with the feature visualization, what we did was we tried to observe the first layer of the convolutional filter. And so given this image, we had the 64 filters, and the good part was that we were able to characterize them into 4 kind of filters. So there were filters which were detecting all the features of the images. Then there were filters which were focusing only on low Euler angles. Then there were filters were focusing only on higher, and then there were filters were just a grain boundary. And the interesting part about this was that in this case, whenever there are multiple filters like this type 4, so all the filters will be active only when they see grain boundary in particular orientation. Otherwise, they will not detect it. So what we can use this so we know what the function of these filters. What we plan to do is that we take the filters and we run them around the hotspot regions and see how these filters are behaving. So can we, in terms of, can the functionality of these filters tell us anything about whether there will be hotspots or not? And maybe we can try something to relate it with the local features of the microstructure. So that is one goal. The second goal was the long range interaction. So what we use is, given the image, we want to find if we have a value at some point, what regions of this microstructure are causing them. So we are looking at various gradient based model, like such as gradient visualization method or something smooth grad, similar to the smooth grad that is used in CNN. And what we ask them is that, let's say I want to find a value at I want to see what regions of microstructure is getting affected by is affecting this value at this point. It tells us something about that regarding the visualization. It tells us that, okay, these are some regions which are actually affecting it and other regions are not. Or similarly, if I take this point, it says that, okay, these regions are affecting it. But right now there is no standard way of characterizing this long range interaction. So this is like a preliminary result, and what we are trying to do is we are trying to come up with some metric to characterize this long range interaction. And it would be very interesting to know, can the model tell us this kind of interactions for our case. So I think I don't want to take more than 40 minutes, but if you guys have any doubt, I would be glad to answer the question. Otherwise, I would just like to close the presentation. So.
Okay, yeah, Ankit, thank you very much for your presentation. So yeah, I have 2 questions. Okay. The first one is that in your introduction, you said that the high stress region are mostly accumulating in the green boundary region, and but I see that in the later deep learning model, you still like use the whole domain as the like area where you want to reconstruct the stress. So have you ever thought of any like other method that limits the domain on those regions close to the boundary, so that you only, like for example, you only predict, okay, which regions are high stress on the boundary or close to the boundary, instead of on the whole 2D domain? This is
So
my first question.
what once we did, as I said, we started with this regression models. And what we did was like we chose our size filter size, where we were not giving the whole image, but we are saying that, okay, we are giving the image around this point, and can you predict the values of stresses, peak stress here? So if I want to predict the value at this point, I'm giving you only these regions. But the problem was that we still don't know whether this region is enough or whether this region is enough, and how much region. There is no answer to the long range interaction, and that's what we wanted to observe.
Okay,
The other thing was, that this hotspots is not just created by this thing, these features, but it is also dependent on the stress values around it. So, so if there are like values that is increasing here, they will keep on increasing, and then there will be a sudden jump. So, so what we feel is that this feature is values still affecting because of the values around it, as well as values around it. That's why we had to go with this kind of model.
Okay, I see. And my second question is that yeah, this model is more based on like data driven. So have you ever thought of anything that incorporates like either very strong or weak physics principles into this? I mean mechanics.
Yeah. So one of my idea was, and like I'm actually working with one professor, with my professor right now. Like we are working on many things. We are looking into things which can help us improving the model. But what we did, so I tried to say something here. What our goal was to make sure that we don't want to predict the stress value exactly. So what we are concerned about is the data driven. Yeah, exactly what you say right now. But yeah, I also sometimes wonder that what if I have included a boundary condition and like some continuity equation would have helped better. It might improve the accuracy, but my whole goal is that I just want to focus. If the encoder decoder doesn't help me answer the questions, there's no point of making it more complex. So it's better to look for some other model that answers my question. So the goal is not to interpret, like predict. The goal is to like interpret and answer some of the questions. That's what the goal was.
Okay, yeah, thank you. And is there any other questions from audience?
Maybe Raj has a question. Raj is doing
yes,
this type of work.
I do. Yes, I do.
With with
yeah.
pins. Yeah, go ahead, Raj.
Yeah. Hi, Ankit. This is Raj from Brown. So on slide 26, you mentioned the orientation. So is it the Euler angle? How did you quantify that on slide 26?
Okay. Okay, so I understand. So this orientation is
how did you quantify it? Is it the Euler angle or something?
Oh, no. So this orientation is the orientation of these hotspots, not the crystal orientation. So so we are characterizing the geometric character. So we are using the geometric characteristics of the hotspot as one of the way to define it. So because like we can see that there is a hotspot, but how do you define it? So we use these three values like location, size, and orientation. So what we do is like we say that, okay, this is our so right now we came up with this metric where we say this is our hotspot, and just find the equivalent ellipse. What will be the equivalent ellipse for this thing? And we just say the orientation of this is almost equivalent to the orientation of this ellipse. But yeah, I understand that this metric is still very sensitive. So like, and we are working on coming up with some better metric, but like, I hope that this answers the question, right?
But what is the physical significance of that? Means I still don't understand that.
Okay, so the reason was that okay, if there is a very large difference in the orientation of the hotspot, And when we are, when at the time of the interpretation, we are saying that, okay, this is our hotspot that model has predicted, we might be focusing on the regions which might affect this orientation. That's what we wanted to see. That if the orientation is wrong, we might be observing some wrong features. We don't want to include unnecessary features which are not affecting. So, and also some intuitive way of finding whether the hotspots are good enough or not.
Okay. The second question I had that, yeah, that's okay. Thanks. The second question I had, this stiffness you have considered constant for the entire domain, the stiffness of the material, the stiffness coefficients.
Yeah, stiffness coefficient.
So
the
does
only
this,
okay.
Does this hotspot affect those coefficients? Like, did you see any variation in that?
So we did not try to change the coefficients right now. I feel so there are like multi-phase. So we have used this single phase microstructure, but if you want to use, so there are papers where they have not used the Euler angles, but they have used this two-phase microstructure, and it also has have been creating some kind of hotspots, but we have not tried in our problem right now. So we are just focusing on the Euler angles for crystal orientation right now.
So the reason why I asked this question, because because these coefficients depend on the Euler angle, though they are same material.
Oh, okay,
so,
okay, sorry.
So that's my point. So
okay, yeah. So I understand that. So what is here the coefficient is, this is a standard coefficient of the elasticity coefficient, and what we do is like we rotate as per the Euler angle. So at the time of generating the data, this matrix will be rotated. I thought you were talking about whether the values.
Yeah.
So this is actually, so this is the main reason. So if you think of if you had this isotropic crystals, this all the grains will have the same orientation, and you will not actually observe the hotspot at all. What you will observe is a uniform distribution of stresses.
Yeah. Thank you. Those are my questions. Thank you very much.
Raj, do you think that hotspots can be detected with the ultrasound?
Yes, we can detect the hotspot. If we can, that's why I was working on the Euler angle dependency of this stiffness coefficients, and they will give the hotspot actually. So
yeah, okay. Yeah. I think some data has a question. I see here she's eagerly awaiting to ask a tough question.
No. So I have a couple of questions, Ankit. Firstly, I wanted to know that you have mentioned about this peak spot or the peak stress. So by peak stress, do you mean that it's like you've taken the gradient, or you've taken the highest stress in the whole region?
Oh, so yeah, we use this peak detection. Peak stresses means like we take a small regions and we say what is the highest value around that region. That's what we say peak stresses.
So suppose you change the threshold. Now you take a lower threshold like 0.5 or something, comparing it against a 0.7 threshold. So you will have less number of hotspots, less number of points to change. So
yes.
Then you're saying that your peak would be like the one that has the highest, but you have lesser number of comparisons. Will it not affect the results?
That's actually a very good question. So this actually affects the results. So it doesn't affect the results in the case of location, because our location is actually characterized by the location of peak itself. So we say hotspots, but it does affect our results in the case of let's say the sizes or the orientation. So let's say here it's very small, right? So if I'm comparing this, a small change in pixel is actually causing the problem. So when we actually, when I discussed this result, we had to actually, so like this is the one of the reason that actually, that's why the threshold, you see this, it's affecting the values here. At the same time, in the case of the here, in the size part, that's why you actually see that there is like pattern is not followed exactly. And even at that time also, I had to actually remove some of the outliers, and we had to focus only on the values which were not outliers. So yeah, that's actually very good question. Like it does affect this. Like these metrics are very intuitive, and it depends on what our observation depends on what we are choosing. So it took a lot of time for me to find out is my interpretation good enough or not, and I'm not using some wrong data points. So yeah.
And I wanted to ask you, like these high stress points, they will be located on the grain boundary. So because there'll be this discontinuity, so you'll have the high stress on the grain boundary. So like, can it be, is it possible, like we just use a detector, like some edge detector or something to detect the grain boundary and compute the stresses just on the boundary? That way, can you reduce the data set?
So this, okay, so if I show this image, it might look, this very nice image, yeah. So like this might look at that the peak is located at the grain boundary, but it's not exactly located at the grain boundary. It's located at like around the nearest to the grain boundary, and it was observed by one of the paper by Professor Roulette. He is also from CMU. So yeah, you can use those kind of detection, edge detection, and all this stuff. But here is the problem. That's the advantage of this convolutional filters, right? Like convolutional filters will automatically extract all those information which you are actually providing by yourself. So apart from your edge detection, what you suggested, you might have to provide more information. Like for example, you might have to provide how far is the hotspot from these junctions. This kind of details also you will have to provide. And the convolutional filters take care of all these things in general.
Okay. And I have two last
Yeah,
questions.
sure.
So the first one is like you are doing a data-driven method. So
Yeah.
in data-driven, if you are not providing you are saying that you are not so what is your target value? You're trying to find out this. You're trying to find out the stresses. So you're taking the output from Dream 3D, the stress values or the displacement, and you're using the using your stiffness matrix and the automatic differentiation to find out the stress. Like how are you compare, what is your input and what is your output?
Okay, so my first output is this thing. We get this image, this microstructure image from the Dream 3D. So it will just provide this synthetic microstructure. Then we have this FFT package, like based on fast Fourier transform scheme. So it will solve this elasticity equation, and it will give us this von Mises stress. So this is the stress image that we are using. And later what we have to, I'm sorry?
You are inputting the stresses to the network?
I'm not actually inputting the exact value of the stresses. So this is the von Mises stress. So this is dimension will be like single channel 128 by 128 cross 1. I'm not actually inputting the exact value of the stresses. What I'm doing is like we scale the values, right? We try to, so one of the thing while you train this kind of model is you need to scale between -1 to 1 so that a model, so we had to scale. So that's why actually I said this thing that we had to destroy the complete original information, and what we want the model is to learn the pattern. Where are the high stresses? Where are the low stresses? That's it. You just learn this thing. We are not concerned about whether they are whether it's able to learn the continuity right now or not, or we are concerned or whether it's following the boundary condition or not. We just wanted to learn the pattern. Because if this model can't tell us about the interpretation, if we can't interpret anything from this model, then there's no point of improving this model. Then it's better that we try something else that helps us in the interpretation. Like you can definitely try including this boundary physics information, the boundary condition, and even the continuity, stress continuity condition. But right now we are not interested in that part.
So what I can, if I'm not wrong, it's like the stresses, the peak stresses that you're pointing out is the peak stresses, like when you have when you have scaled your stresses from -1 to 1, you're saying this is the peak stress location, but you're not giving the output of the peak stress. Like what is the peak stress? You're not giving that.
Okay, so Can you repeat again?
You said that you have detected, since you have scaled the domain, you have scaled your stresses from -1 to 1, and now you are trying to locate which is the hotspot and the peak point of peak stress.
Yeah.
So you are telling me this is the peak stress point, but you're not providing what is the peak stress point, what is the maximum stress?
Yeah, I'm not providing what I'm saying is I want to find the location, the size, shape. I don't care about the values. I just want to find out where this hotspot is going to be and what part. Right now, this is my goal.
Okay, thank you. These are
okay, thank you.
And Kit, that can you next go to the next slide where you have you took the gradient of the boundaries, right? That was to get just here, yeah. Minlang, I think this would be really interesting also for you, right? For the dissection problem.
Yeah, but I think
that's
the
like
geometry
an extra
for
information. You had to put the displacement, or some the damage, whatever.
Yeah, but yeah, I agree. But the pattern in the arterial wall of a murine is more complicated than this. But this certainly can help. Yeah, it certainly can help.
And Kit, you use Dream 3D. Last week we had as a speaker Somnath Ghosh, who actually developed this. But did you do 3D or in your thesis? Are you going to do 3D in your thesis, or these are 2D images? Is this all 3D or actually 2D images?
So this is a 2D domain, but a 3D crystal. So it has the Euler angle of.
For the triangles. Okay. So it's the real problem. Raj also is using that. Okay, I would like to thank both speakers today. Just some information about Crunch. Crunch, as you could see, is a big group. We're interested in theoretical aspects, from optimization to approximation, to PDEs, to ODEs, to multi-scale modeling. Also, we're interested a lot in different applications. Some people are interested in mechanics, some people are interested in other applications and so on. But that's kind of, we have about 15 postdocs in the group. It's a big group for applied math. But thank you very much for agreeing to give the talks today. And take care, everyone. And Rui, do you want to finish today's meeting?
Yeah, thank you. Thank you again for the two speakers. And this is all for this week's Crunch seminar. And have a good weekend, everyone, and see you next week. Yeah.